All right, this one, it's not in the book, but it's a good example that we're going to do. There's ones like it, so you'll have to do these in some of the math 3 physics. But what we have is we have an inclined plane here, tilted at 25 degrees, with a block that has an initial velocity going up the inclined plane. We have the kinetic friction between the block and the inclined plane, and we want to know how far it goes up the inclined plane before it stops. Okay? So that's what we are trying to solve. So what are we going to do first? We always start first with our free body diagram. So I'm going to create a free body diagram here. We have gravity always going down. We have a normal force, which is always perpendicular to the surface. We have a friction force. Since it's going that way, the friction force is going this way. And because it's already moving, it's kinetic friction. All right? That is all of the forces acting on that object. Now, we have to make our coordinates match the motion. So the motion is up the inclined plane, so I'm going to make this our x-axis. So this is our x-axis, and right along the normal force is the y-axis. Then we have to take the components of gravity, we're going to call this theta here, so that we can solve it. So I'm doing step 2. I'm taking the components because gravity is not along either of the axes. So I have mg cosine theta going down, negative y direction. This is the negative x direction. Mg sine of theta going backwards. Okay, so now we have all our forces on one of the axes, so we're going to do F net. Now we have to look at this. F net x is this way. Notice that it's not balanced. Both forces are going this way. There's no balancing force, so it's definitely accelerating. So I'm going to put here we have minus friction and minus mg sine theta. Why is it minus? Because remember, positive x is this way, that's negative x. But I'm going to replace F net x with ma because it's accelerating. So ma is equal to minus the friction force minus mg sine theta. Don't put this in as negative, all right? Put it in just as ma. A is going to come out as being negative, but that tells you the direction of the acceleration. Just put it in as ma. Don't put in negative ma, okay? All right, now the problem is I can't solve this. But before I do this, I'm going to expand this. Remember what we decided to do with friction is we have to replace that with mu sub k times the normal force minus mg sine theta. All right, now I can't solve this because I don't know the normal force, I don't know the mass, and so I can't solve that right now. I need to solve for the acceleration. But I can do F net y. And F net y, look over here, I have positive normal force and minus mg cosine theta are the two forces on the y-axis. But in the y direction, it is not accelerating. It's not going flying off of the ramp, it's just going up the ramp. So there's no acceleration in the y direction, so I replace that with 0, and I can say, oh, well, the normal force is just equal to mg cosine theta. Then I'm going to plug that back in right there, saying normal force. So this becomes ma, so I'm rewriting this one, ma is equal to mu sub k times mg cosine theta minus mg sine theta. Then I'm going to divide both sides by m. Notice the m's go away, which is really good because I was never told what the mass was. And so when I rewrite this, I'm going to get that the acceleration is equal to, I got to be careful, I almost lost the negative sign there, minus mu sub k g cosine theta minus g sine theta. And that tells me my acceleration. Remember, way back in chapter 4 we did inclined plane and I told you the acceleration was equal to g sine theta. If there was no friction, this would be 0. That term would go away, and acceleration just becomes g sine theta. That's where that came from. It's the acceleration just caused by the gravitational pull on an inclined plane is g sine theta. You multiply that by m, you get it into a force. All right, so remember the negative just tells us direction. That just means it's going to the left. I know all those numbers, so I can multiply this. I can factor out a g, but it doesn't really matter. So I'm just going to put these in. 0.45 times 9.8 times the cosine of 25 minus 9.8 times the sine of 25. So the acceleration is equal to minus 8.13 meters per second squared. Yeah. But that's not what it asked for. What it asked for was how far it goes up here before it stops. All I do is figure out the acceleration. If I have the acceleration, I have the initial velocity, so I can use one of my constant acceleration equations from chapter 4. I'm going to use this one. V squared is equal to V naught squared plus 2a x minus x naught. Now my final velocity is going to be 0 because it's going to stop. And I'm going to solve it for x. My initial position is 0, too. So I just want to solve that for x. Or what I'm going to get is that x is equal to, I'm going to move that over here. This is going to become minus v naught squared over 2a. Is going to be what that is. Don't worry about the negative because remember a is negative. So the negatives are going to end up canceling, give us a positive value, which is what we want because x is going up. All right, so we're going to have minus, our initial was 4.5 squared over 2 times negative 8.13. We get that the block goes up a distance of 1.24 meters. Or we only have 2 sig figs, so 1.2 meters. All right. The good thing about that example is it shows a problem where you have to use the acceleration and that you have to do an inclined plane and get components and you have to deal with friction. So this is a good example to show the things that we need, all the different parts we need to know for chapter 6.